Hey everyone, so we're going to keep going on with kinetics, and this time we're going to be talking about the integrated rate law. Like I said before, the other rate law is all about how concentration relates to the rate. This is going to be about how concentration relates to the time. So let's kind of move on with this real quick. All right, so concentration versus time. That's what the integrated rate law is all about. So you might have a problem like this on the screen. What is the concentration of A in 200 seconds if we start with 1.4 molar? Simple enough, right? And you might think, okay, we can go through that. I mean, I know, the rate law of things. So you can say the rate equals the rate law constant, and this is the concentration of A to the first power. Let's say that's the thing. And remember, this concentration is kind of what we started with. So that's our initial concentration there. And what are we looking for? We're looking for the concentration at 200 seconds. So this is concentration at time 200. Where am I going to put the 200 seconds in here? I don't know. Okay. I got a problem. I don't know where to put it in the 200 seconds. It's fine. We can't use this form of the rate law because this form, the differential rate law, is all about the initial concentration and how it affects the rate. This is not about time and how it affects the concentration. So, even as you can see down here in these graphs, we have concentration versus time. We don't have a thing for time up here. We have one for rate. So what we're going to have to do is pull time out of the rate, the seconds. Remember, rate is just molarity over seconds. Rearrange all of this using calculus to come up with a different form of the rate law instead of the differential rate law to the integrated rate law. Don't worry, I'm not going to expect you to do calculus. Okay, you won't have to go through and do one lick of calculus for this. All right, don't worry. I did all the math for you, and here it is. So if you have a zeroth order reaction, remember what that looks like. That's where rate equals the rate constant. And you might have your A here to the zeroth power, but remember this is just 1, so rate equals K. If that's the case, then this is going to be the equation you use, the integrated rate law you use. And you may notice that on your constants and equation sheet, these are all there. So don't worry. There's that. All right. So in this case, you could go through and say, okay, I got my K, and I know T is going to be 200 seconds. And my initial concentration was 1.4 molar. Now I can go through and figure out what the concentration at the time is. So that's a lot easier. That's a lot easier to kind of plug and chug. I don't have to worry so much about doing the calculus. I just have this. But this is for the zeroth order reaction. If it's first order reaction, it's a little different. This is the natural log of the concentration equals the natural log of the concentration at time 0 minus rate law constant, and then time, whatever time you're wanting. So there's that. And then second order is going to be the reciprocal of the concentration at time, 1 over concentration, equals 1 over initial concentration plus K, rate law constant, T, time that you're after. You may notice that all of these are that line graph form, that y equals mx plus b form. And if you kind of look here for the first order reaction, y is going to be our natural log of the concentration of A. Our slope is the rate law constant, or the negative of the rate law constant. That's going to be helpful to us. X is going to be our time, which is kind of what we're after. Our y is going to be ln concentration of A, and then x is going to be our time. this is exactly what we were after, right? This is exactly the type of graph that we are after here. Okay? And then B is our initial concentration. So we know that where it crosses this line here is going to be our initial concentration. And then throughout time, it's going to move down. We can just see where it ends. All right. So that's that. This is going to be the equations we're going to use to figure out the concentration at a specific time. All right. And this is also another cool way. It's cool, guys, I swear. This is another way of figuring out the order of the reaction. If you're given a whole bunch of concentrations and a whole bunch of times, and you plot them out, if it makes a straight line, whenever you just do concentration versus time, you know that the rate's not changing. The rate is not changing with this concentration. If the rate was changing with this concentration, it would kind of look something like this. And since we know the rate's not changing with concentration, we know this is a zeroth order reaction. So it's a straight line whenever you plot it like this. It's a zeroth order reaction. If it's a straight line when you have the natural log of concentration, then you know it's a first order reaction. And if it's a straight line when you plot it with the reciprocal 1 over concentration, you know it's a second order reaction. So this is going to be helpful to us. It's going to be helpful to us to figure out what order these things are going to be. And then also, if you're doing it this way, this is a great way of figuring out what K is as well. So this is a second way that we can figure out K. All right. A little bit of practice. So looking at these three, it's the same data, just plotted differently. This is just normal concentration versus time. This is the natural log of concentration versus time. And this is the reciprocal of concentration versus time. Now what you're going to be looking for is, which one is the straight line? Well, it's pretty obvious. This guy is the straight line. So if you remember, if it's the just concentration versus time, it's zeroth order. If it's the natural log of concentration, this is your first order. And if it's reciprocal, second order. So we know that whatever reaction this is, we know that it is second order. And if we wanted to look at the slope of this line, we know that it is the rate law constant. We know what that little k is now. So there's that. Let's kind of start putting this in it. I'm going to give this to you. This is a little cheat sheet. You won't be able to use it on the exam, but it can help you with studying and things like that. It has the integrated rate laws for these guys. It has kind of what the concentration versus time plots look like. Concentration versus time plots look like here. Your relative concentrations. So if it's a 1-to-1 change, it should be 1-to-1. If it's 1-to-2 change, it should be 1-to-1. 1-to-3 change, 1-to-1. Yeah. So on and so forth here. This is a nice little cheat sheet. It also includes the half-life, which I'll get to later in a little bit. All right. So you can see the kind of how I might go about asking you some of these questions if I wanted to be a real big jerk and give you kind of one of these marathon kinetics problems. So I can give you some experimental data, and I can say, what's the rate law of this? What order is this reaction? And then you're going to have to go through and then figure out, remember that's like, oh, this is, twice, and this is times 4. So then the concentration of A is to the second, and this one is, you do the same thing. It's like I doubled this, and it didn't change at all, so this is zeroth order. And then there's that. And then you can, plug in whatever these numbers are and figure out K. Once I have K, I can ask you, like, okay, at 200 seconds, what is the concentration going to be, so on and so forth. So yeah, you can see how I can say start out by giving me the differential rate law, and then I give you a time and ask you to use the K that you found to give me the concentration at a specific time. So another thing you can do is think about half-lives. So since half-life is, just to make sure everyone remembers what a half-life is how much time it takes for exactly half of the thing to go away. So let's say I start with a 1.4 molar. How much time has to pass until I have 0.7 molar, exactly half of it, for it to go away? So here are the equations for that. I think the only one, the one that you should know, you should be able to kind of figure out, is the 0th order reaction. You start with something, you divide it by 2 and the rate, and that should tell you how many seconds you have. There's no funny business here. It's just kind of how long does it take for it to reach a half. Whereas the first order reaction is a little bit more involved. There is a special number here. It has to do with that natural log, 0.693 over K, and then that will tell you what the how long it takes to reach half. Second order reactions, I don't even think AP really asks this at all, so don't worry about that. These are all going to be on that little cheat sheet that I give you. And here you can just kind of say, what is the first order reaction that has this K? What's the half-life? It's pretty simple. Just remember T, the half-life, the time to get one half-life is going to be 0.639 over K, 5 times 10 to the negative 5th. And then just do this calculation, and then you'll get your half-life. Easy peasy. All right, guys. Have a good one. See you later.